Okay, so before we start, first thing that some of you guys are asking whether there's a solution. Actually, in each week's weekly material, I posted a solution, even though the solution is from fellow students. Some of them even from previous semester, and I talked to the student there, and he thinks it's okay. So with that being said, one of the reasons is because last time Pasha actually suggested me to see if I can find solutions from lecture solutions from the the instructor's book. Yeah, actually, I got the instructor's book, but it's still in the department. I didn't get it. That's number one. Number two, I don't think they would provide detailed solution in terms of the code. Number one, for this particular book, I don't think they recommended R. So essentially, even if we have a solution from that particular instructor's book, I don't see the the Yes, actually, I forgot to mention that this morning. I mean, last time when I started the grading, I should have told you that there is a solution there for each week. So another thing is really apologize for the delay for this semester. Is my work is just a little bit hectic in the past 2 months, and then things just got delayed significantly. Um, Ideally, I should be posting the solution every at least maybe 2 weeks later. So if you didn't get a chance to read some of them yet, I encourage you to do that. Number one, even though you get 100%, it's probably I give you 100 as a grade, but probably your solution is not perfect. So what I'm saying is it's always a good process to learn from others. So you can take a quick look at your solution, take a quick look at other solution. It probably spend like 20 minutes for maybe less than that for each homework. Then you would benefit significantly from there. So that's a suggestion there. And then that's that. Do you have any other questions on the homework on this regard? And also, I just want to mention that if you have any concerns or any questions regarding the grade that you got, send me an email so that we can discuss. Um, so we can go from there. And if you don't have any questions on the homework, I just want to quickly move on to the project. So no questions so far. Then for the homework, for the project, as I actually initially said, we should have a draft proposal and then have a final proposal, which was due last weekend. And then if I know that I also delayed that process, discussing, giving you some feedback on the proposal, a draft proposal, which actually I did probably last Friday. I hope you actually got that. And then for some of the teams, I think the draft proposal actually looked fine. Um, so Haley, I'll address that question a little bit later. Okay. So and then for some other teams, actually, I have some suggestions, and then mainly it's coming from the idea that if you have two-person in a team, you probably just need to finish two, at most three. If you finish two pieces, that would be fine. If you only have one person in the group, you can just finish one or two. So why would be sufficient, but if you have extra time, you want to finish two, that would be fine too. But if you have two people or three people on a team, I don't really encourage you to do that. Okay, I have three people on the team, and then each of us responsible for one. That's okay. You can start with that, but at the end, you should discuss, communicate with each other so that you can learn from others as well. And then, as a team, when you present the final solution for your project, remember you have a presentation that you need to go through, and then hopefully you can all know each other, what each other has done, or it's more like essentially I want you guys to do as a team effort instead of an individual projects. That's from that front. And and then because we have a lot of students for this semester, I think we have around at least 30 students. So even though meaning that we have at least 10 or more teams, 10 to 15 teams, so we wouldn't be able to finish the presentation in one session. We probably have to do that in 2 sessions. Good news is that we don't have a final exam for this course, so we could focus more on the final presentation on this particular on the projects. So in terms of the projects, do you have any questions? Okay, no questions. And then let's quickly take a look at our plan. You can see my screen okay, right? Okay. So project presentation slides due in December the 10th, which is like a month from today, 4 weeks. So which is Thursday 8 p.m. And then because we have a 8:15 presentation, so starting from December 10th, 8:15, probably first group can present. But I kind of feel that we probably have to delay this report due to the next week, the following week. Yeah, let's put it this way. There's a chance that we can. Let me see. Yeah, most probably won't. So what I'm saying is December 10th would be the first time that we have. December 10th would be the first time that we would have that presentation. And then the following Wednesday, which would be supposed to be the office hour, we can use that time for the presentation as well, which would be December 16th. And then correspondingly, let's say that the final project report will be due on the 20th, which is that Sunday. So so that's that. So in terms of how long that presentation should be, if you have one person, let's try to limit it to 5 to 10 minutes. If you have a team of 3, let's still manage it to be like 15 minutes, so that we can go through as many as possible. So I think it's a perfect opportunity to learn from other teams. Unfortunately, this semester I don't see a lot of projects that's out of the textbook. I actually would think that it's probably more beneficial to yourself if you do some more real problem in industry setting or real types of project there. So if you have a group of 2, I think you can just limit the time to be around 10 minutes. So essentially, this is not a hard cutoff. So for one person, 5 to 7 minutes. For 2 person, maybe 10 to 12. For 3 person, probably like 15 to 18 minutes. So let's try to mix that way. Okay, so I'm going to send out another detailed plan on this project presentation and also project report revised timeline on here. I'll send you an email so that you are aware of that. And then on the other end, I know everybody probably finished all the 14 assignments. And then if you haven't done the online discussion, please do that. Actually, this semester, I found that each of you are trying to get a new thread, which is less than ideal. But again, because my busy schedule didn't get a chance to monitor better on that front, what I was really looking into is more like each week everyone is engaged in the discussion to comment to each other's post not necessarily, even you say, okay, great comments, things like that would be considered to be some involvement. So if you didn't submit the online discussion yet, please do so, even though I actually take off some, um, of the, if you are being late for the discussion, I take off some points because otherwise it wouldn't be fair for the students who actually submitted on time. So that's something that I need to communicate it. Okay, so let's continue. I know that we missed last session. We were not able to make it, and then I know that we might be missing one session. Oh, this is something that would be Thanksgiving, I believe. Not here. Yeah, for the session that's coming up, which is November 26th, I suggest we probably move to November 25th, which is a Wednesday. So I'm going to send an announcement as well, and hopefully you guys can make it. If not, I'm going to record the session anyway, so hopefully that will be helpful. And then after 25th, next meetup will be already around the 10th, which is the final presentation. So we'll see if we will be able to cover everything that we plan on. If not, we probably add another session in between 26th to the 10th. Essentially, that's the basic idea. So we lagged behind in terms of the progress. We have week 9, 10, 11, and 12. Today, let's try to cover week 12 and week 10, 11, and then we can leave week 9, which is a game theory, for some time around the next time, which is the 25th. Okay, so I'll start off from the week 12 material, which is for this week. So before I start, do you have any questions? Uh, so Haley, I'll try to address your question a little bit later for that gradient descent um, problem. Okay. And then so continue with okay, let's continue with this. Yeah. Okay. So continue with the mathematical modeling techniques for uh, continue with the week 12. So the basic idea here is in chapter 7 we study linear program. So everybody, I look at the homework for that particular section. Apparently, you all did a good job there. You understood what is a linear program. You know how to use simplex, you know, in one way um, to solve the problem. And then also, and then in the integer program, in the supplementary texts that I provided, I hope you realize what that is. In the syllabus, the supplementary text is this text, which is an online book. So you can use this book and take a look at the integer programming. It has a very detailed discussion on integer programming. And then for integer programming, that's chapter 8, which is text. And then this section actually, the chapter 13. I mean, this week we're talking about nonlinear programming. And then I believe next week we actually started week 14. We have information on integer programming. Let me quickly confirm that. Yes, next week would be covering integer programming. So this week we're actually covering nonlinear programming. And then there's an example on the textbook which is talking about minimizing the cost of delivery and storage. And then I said that this can be solved using calculus. Essentially, for a quadratic program, quadratic objective function, what you can do is you take the first order derivative equal to 0, and then second order derivative equal to 0. You can set the minimum where the minimal starts, right? So that's one of the part. And then you can imagine that for a lot of supply chain type of problems and a lot of um, e-commerce companies, they have this problem in terms of trying to minimize overall transportation cost and storage cost. Sometimes they also have some other costs in place, such as unmet demand. If someone's demand is not being met, then we lost some sort of revenue that could be in our objective function. And then let's say for this particular methods to, and then let's say for next example, we talked about methods to optimize functions of several variables. And then suppose that we have a max revenue. Revenue is P1 x1 plus P2 x2, and then P1 is this. And then as you can see, because P1 is a function of x1 and x2, and then we have an objective function that is x1 squared. And then on the second component, we have a x2 squared, and also you have a x1 times x2 on the second component. Similarly, on the first component, you would have x2 times x1 as well. So that's why it now becomes a nonlinear function instead of a linear function, right? So, and then we subject to certain constraint. This usually would be some sort of budget constraint or some sort of capacity constraint. Okay, and then if, as I mentioned just now, if we set the first order derivative to solve the problem, what we can do is take the partial derivative of the x1 and then set it to 0, and then take the partial derivative of x2 and set it to 0, and then we can solve for x1 and x2. And then what we do is for the second order derivative, if we can continue to set the second order, if we can set the second order derivative equal to 0, and then we can confirm it is maximum. If it's larger than 0, and then we know it would be a minimum for the whole solution, for the whole problem. Okay, and then let's say how we can calculate the gradient method of steep ascent or descent. Okay, if you're asking this question, it's essentially meaning you haven't taken IS605 yet. That's okay, but I was referring to Appendix B. I think it's in the textbook, but I'll confirm right after this lecture, and then I'll send you an email and announcement regarding where that Appendix B is. It should be in the textbook though. And then the reason I'm saying is because this method is actually we studied in IS609, which is computational mathematics, which is supposed to be the prerequisite for this particular course. So if you haven't studied that yet, I'm sure you will study that next semester. But for this semester, for this particular question problem, you can point to the right direction to find out some simple reference so that you can use it there. So the basic idea is use a function to take a partial order derivative of a particular variable, and then use certain step size, which is called lambda k, starting from a point, which is xk and yk. Use lambda plus a certain step size. You move towards the gradient descent direction using a certain step size, which is a lambda, to try to evaluate your new function value. That's the idea. So using the same function value move your x for a little bit to see what's your g lambda. So that's the basic idea. But I'm going to point you to the right reference right after this session. And then we studied method to optimize functions of several variables. One of them here, we studied nonlinear least squares. Remember that for the regression, linear regression, basic idea is trying to minimize the projected value minus the actual value squared and sum all the error together. And then we're trying to minimize the sum squared error. And then in there, what we did was the same thing. We take partial derivative on both parameters A and B and get the solution for the minimization problem. So linear regression problem needs to be solved as a nonlinear problem. So that's the connection between linear regression and nonlinear programming. And then later, if you actually studied a little bit of machine learning, or if you have, I know some of you probably already taken the Coursera machine learning course in the summer. So if you have done that, you would realize in many of the machine learning algorithms, they are fundamentally nonlinear programming problem. For example, support vector machines. Support vector machines is a quadratic programming problem. We're not saying that when you meet those type of problems, you would be able to know how to solve it exactly, but you would get a sense and know where to find the reference. For example, SVM itself is a quadratic program. It has two components. One component is complexity of your learning algorithm. The second component is the fitting function for your data. So if you know that, and then you know how to solve quadratic program, then you kind of get a sense roughly on how these all pieces are connected with each other. So continue with this conversation. If we have a constraint continuous optimization, so we want to minimize a specific function, and then so that this particular constraint is met. One of the approach is called Lagrangian multipliers. The method itself is not that difficult. Essentially, we say, okay, use a Lagrangian multiplier that is called lambda. Start with to set up this L function, which is the Lagrangian function, which equals to the objective function plus lambda times a transformation of the constraint, which is, if you look at this follow-up here, is lambda times the left-hand side minus 24. So essentially trying to set up the function so that we have a Lagrangian function, and then we try to solve L. And then what's the approach for this Lagrangian multiplier approach? It is similar to what we just mentioned. You take first order derivative to take first order partial derivative to each individual variable, including your lambda, because lambda itself is some sort of variable that we introduced to set up the Lagrangian function. So in that case, if we set those three partial order derivatives equal to 0, we will be able to solve x1, x2, and lambda together. And then after solving x1, x2, and lambda, we know the objective function would be a specific value. And then the book specifically mentioned this part because earlier in linear programming, we studied something on the sensitivity. When you move your x, what's the corresponding change to your objective function? And also another type of sensitivity would be, what if you move your increase your right-hand side, increase your resources? What's the corresponding change of your objective function? And then in this case, we say that the solution actually represents shadow price. The amount of the objective function would change for a unit of increase in the constraint represented by lambda. So that's interesting observation there. If you pay attention to the textbook on this section, it's some useful information there, I believe. So go ahead and definitely dig into that. And then the textbook has another example, which is space shuttle water container. And then as we can see, similarly, we have objective function, we have certain constraint, and then we set up the Lagrangian multipliers approach, which is objective function minus, it really doesn't matter if you use minus or plus lambda times this one minus 450. So with that being said, you can use 450 minus the left-hand side and then plus lambda or minus lambda. Either way, it would work because what you really do is trying to take the partial derivative, which doesn't matter here if it's positive or negative in terms of the coefficient for the lambda. And again, similarly, we got the solution. Okay, this is total surface area is increased by 1 unit of volume of the water container, increase approximately 3 cubic meters based on this lambda. So essentially saying lambda itself is a shadow price. And then what is shadow price? Shadow price is the right hand, what if you increase right hand side by 1 unit? What's going to happen to your objective function? Okay, that's something that we studied in linear programming for the sensitivity analysis. Two types of sensitivity analysis. One type is if you increase 1 unit of x, what's the change of the objective function? And then second one is if you increase one unit on your right hand side of your resources, what's going to happen to your objective function? So that's second type is called shadow price, which is actually connected to economics itself as well. If you actually study economics, you would realize that macroeconomics itself is a set of optimization problems, meaning that you're trying to maximize some sort of economic profit subject to certain constraint. And then even from social economics perspective, the overall social economic benefit itself can be modeled as an optimization problem. And then if we think about some other issues, for example, transportation in the transportation networks, we have a specific problem. It's called social equilibrium. So social equilibrium itself is saying that every single person, traveler, is trying to find the shortest path in a network. And then as a result, the overall network is not optimal, right? As you can imagine, right? Theoretically, if all of us is trying to pick the shortest path, and then shortest path becomes very crowded, and then the whole network is not best used, right? And then if we try to maximize the overall benefit of the whole system, then the result should be not every single person is trying to find his best path. And then it's called system equilibrium versus user equilibrium. Similar idea actually also exists in the economics field. So if you happen that you studied macroeconomics, it would be nice that you know this. If not, in the future, if you get a chance to study macroeconomics, you would realize the importance of some of this approach and some of these formulations that we discussed here. Okay, continue with this. And then this is also very similar to what we just did, trying to take the first order derivative and trying to set the first order derivative to 0 and trying to solve the problem. And then specifically, I mentioned this model interpretation. That's because I think this particular example is very interesting example that you should go over to understand how the model is applied and how it is used. Okay, without further ado, overall, I actually covered the major topics for this particular chapter, and then these are the homeworks for this particular week, and then I can continue. Yeah, let's quickly go through the gradient. But I thought this gradient, I don't know why you guys are asking about this B. I thought it's actually only on the week 14. No? I know in week 14 we talk about page B. Okay, that's page, that's week 14. So which one? Oh, week 13, I believe, right? Okay, hold on. Okay, hold on, let me go to the textbook. Okay, at the moment I cannot access. At the moment I cannot access the textbook, but I'll check that right after we finish the lecture. Okay. Okay. So let's continue with week 10 and week 11 materials today, and then after that I'll come back and look at the appendix B for you guys. And then, by the way, next week, week 13, we are covering one is the graphs models, and then after that, actually, we are going to cover a little bit on the integer programming for the 25th session, say. Okay. So let's go to week 10, week 10 and week 11. Okay. So okay, so the reason that we can discuss week 10, week 11 together, as you probably know, is because both of those two sections are using differential equation to model some of the real life problems. So in chapter 11, there's some discussion in the textbook on the population growth, prescribing drug dosage, and the breaking distance revisited. I know earlier when we studied difference, we used that example, and then also graphical solutions for autonomous differential equations and numerical approximation methods, separation of variables, and linear equations. So let's say, so we started actually difference equations. We say that delta p is defined as p t plus delta t minus pt, and then this can be approximated as kp delta t. And then if we use a limit t approaching 0, delta p divided by delta t can be approximated as dp over dt, which is kp. So the derivative as a rate of change. So it's actually not new if you think about the tangent. At any of the points, the tangent can be approximation. If we add all the tangent together, move along the line, we would have the whole thing, right? Even though we say that if we really just use tangent to do approximation, it's probably in some cases can be a little bit rough. So derivative of the slope of tangent line. So it's the same basic idea here. From this graph, actually, it essentially tells us that depending on how small your delta t is, the approximation can be very rough. If delta t1 is really big, then this approximation, as you can see, the graph itself versus the tangent, it's harder to do a approximation. And then for the population growth, in that example, essentially saying that there'll be some new births. Meanwhile, there's some people that actually lost their lives. So there's a certain probability or certain rate for the population growth, so that we can model that population growth problem itself as a differential equation, and then we use delta p divided by delta t, so that we would be able to solve the population growth problem. Even though, as you know, that for any of the differential equation, you really need initial condition. As long as we can set up the initial condition, we would be able to solve the problem, find the function form itself on pt equals p0 powered by this e powered by something in this particular example. So with this being said, as you can see that we have been using so many types of techniques in this course. We have studied decision tree, we studied differential equations type of modeling approach. We studied linear programming. We studied simulation. So we studied linear regression. But the whole idea here that we're trying to convey is when you have some sort of problem that you have in your at your work, and then you're trying to solve it, you kind of have an umbrella of all types of methods that you can think of, and then start thinking, oh, maybe one of the approach that we studied here can be applied there, and then you can try to model the problem as a math problem. Even though it's not to say that all the problems formulating by math models would be better solved. That may not be necessarily true, but even though we should remember that with some sort of math model, you would be able to understand the real problem probably better, so that you have a more informed decision. The whole purpose of all these math models is trying to decision support any of the decision or real problems that you are trying to solve. Actually, one student was thinking that whether he should use decision tree to make a decision on switching a job. I think that's actually why not? It's definitely worthwhile to take a look there. Okay, because you had some discussion regarding what you guys want to get out. I have a discussion topic last week, I believe, or week 10 or week 11, asking what your plan in terms of after the MSDA program, and then what's the motivation for getting into this program. So I think based on that comments, looks like a majority of you think that you learn a lot, even though I think one of the, to be honest, when I was looking at some of the curriculum or syllabus or overall curriculum design, we probably have some overlap in some of the courses. And then in many of the courses, probably in the place that we would be able to dive a little bit deeper, we probably was not able to do that yet. But overall speaking, because number one, the program itself is still new, and then majority of the faculty members are still trying to get together to think more and try to make the program better. That's a little bit further for the discussion, but let's continue with this. So another example here, given trying to refine the model to reflect limited growth, because we realized the model has a fundamental problem that it doesn't have a cap in terms of rate of population growth. So in that case, not the rate of the population growth, but the overall level of the population. So in some of the real examples that you experience in the industry problem or real work problems, you would have this issue as well. You have to cap somewhere, and then you can better solve the problem. And then continue with this, we see that it's still a different equation problem so that you can solve it. And then similarly, we have more examples in the textbook on the drag dosage, on the braking distance revisited, and graphical solutions for autonomous differential equations. So, and then the book actually specifically mentioned that maximum braking force increases in proportion to the mass of the car, resulting in the same solution as in section 2.2, from different perspective looking at the same sort of problem there. And then there's some other graphical methods to look at the autonomous differential equations in the textbook. If you haven't read this part, it's a very interesting section. Actually, I read this part as well. Very good. Overall, I think the book is well written. Definitely worthwhile for you guys to read it. Even maybe on a train ride or on anything, it's worth something. Since you're in the program, it's good that you read the book. And then numeric approximation here is actually specifically talked about Euler approximation. We have homework actually related to this section. So essentially, if we the basic idea is if we use some sort of I need to highlight. Hold on. If we use some sort of linear approximation or using Euler's method, which is uh, some tangent line gradient type of method to approximate the original function, then we can use Euler's method to approximate. So overall speaking, as we can see here, three pieces linear function is actually, in this particular case, is not doing really a good job. But in reality, there's some other better methods. If you have, what about you have 15 pieces of this? Then essentially you would imagine that it would go from here, here, there, and it would be very close in terms of function form itself. So Euler provided a numerical approximation to solve the problem. And then the book talked about separation of variables. And then it's more, and here we are talking about how to solve the linear first order equation in standard form. So we actually need to read the appendix. I believe that's probably ALP, but I'll review that there. Appendix A itself, I think, is regarding the some of the solution method for first order equation, and then standard form essentially what it's trying to figure out is you only have first order derivative on the left hand side and also the variable itself on the left hand side, and on the right hand side specifically only have a function related to x, not y. And then based on that, you can solve it using the following approach here that I presented here. And then I think that's pretty much, oh, even though there's some more examples on how this is solved, and then uniqueness of solutions, and then that's pretty much it for this particular section. And then if we continue with week 10, is that week 10 already? Yes, I believe so. Okay, if we continue with week 11, and then there's a continued discussion with graphical solution for autonomous system of first order differential equations. And then there are some examples: competitive hunter model, predator prey model, two military examples, and also Euler's method for system of differential equations. For this chapter, it's actually major focus is on the 12.5. The majority of the first 3 or 4 sections are more like specific application examples. So we don't really have a lot of to discuss here. But one thing that you probably already studied, how to special system that involves two first order differential equations. Can we see the alternative? How can we see whether the solution is stable or not stable? And then on page 526 and 527, you have specific 2 examples on that. Here, actually, I don't really have a lot of insights that I can discuss. But overall, it's just whether starting from the starting point, whether with time goes on, whether the solution is going to be a function of the time t. If it's a function of the time t, then it is not a stable rest point. Otherwise, it is a stable rest point. So that's very same thing. Yep, that's pretty much actually everything that I plan to cover for this week. And as I said, we're going to meet on the 25th. Before you guys go, let me continue to search the the page B that we that you guys are asking. If any of you actually know the answer, please feel free to jump in. Okay, so let's go to the textbook. Yeah, I really couldn't remember what I did, why I used page B13. So let's say graphical functions. Oh, it's really here. I don't, um, maybe the textbook changed or what? Here, see the chapter 15. Chapter 15 is supposed to be graphs of functions as models, which is this chapter 15 that we saw here. It is page B here. So I don't know, unless the textbook changed this year, I don't see any reason it would be. We're looking at the same version, same edition, I mean. So if we look at this particular example, page B13, number 4 is right here. Oops. Can anybody confirm a textbook? So essentially, page 5, I mean, I say page B essentially is chapter 15. The only possibility would be, sorry, after, okay. Okay, so Okay, so guys, I think when you guys are discussing this, I didn't catch, but it really, essentially, this page B, as you can see here, I'm not sure if you can see my screen there. So I mean here, see my mouse. It's page B1, right? Page B2 here. So that's why when I was using this as a reference, it's really on the chapter 15. It's called page B1, B2, but it's really probably just 15-1 supposed to be. See, okay, for chapter 14, used page A somehow. Okay, so that's actually explains. For chapter 15, it's page B something. So essentially, all those page B is chapter 15. Okay, B13 number 4. B13 number 4, right here, which is chapter 15, number 4. Nuclear, yeah. Okay, I'll do that. I'll do that so that everybody knows. Okay, great. Um, so that's pretty much everything. Again, for the homework grades, you guys should take a look, and then if you have questions, let me know. And also for the solutions, you definitely should take a look at the fellow students' solutions there, so that you know where you are missing. Again, I'm trying to get the textbook, instructor's textbook. I don't think it would be as useful as fellow student solution after all, because it wouldn't have any of the R coding there at all, because this textbook never mentioned R at all. It's only more math oriented instead of for this particular program in MSDA program for this course, we kind of used R in conjunction with the textbook, so it's somewhat unique in that sense. Okay, without further ado, I think that's pretty much everything for today. And then we're meeting on the 25th, which would be the Wednesday. And I'll talk to you guys soon. If that date doesn't work, we'll figure out something else in that week, earlier that week, maybe Monday or Tuesday. Exactly, the code doesn't have code examples only just because they were not using R at all for this textbook. Um, okay. So Haley, maybe okay. I can quickly do some search for you, and then I just need to go to the textbook. Let's go to.
Hi, I'm referring to the table on page 582.
582. Okay.
So,
Okay.
I mean, how the fifth column is calculated, I cannot do the calculation. That's my question.
Okay. So here you can see that here is specific said that once you set this. Okay, here is specific said that once you set this relationship up, you can use first order derivative to solve for lambda. However, in most cases, we can't easily solve the problem. Moreover, the equation may not have a unique solution, right? So that's, you notice that. And then let's look at here what they did here. For this function, using the starting point, lambda 0 is 1 over 16. So here is specific says that lambda k is 1.2 times lambda k minus 1.
No, I got that one.
Yeah.
I'm asking like how the delta p of x1 and y1 is calculated.
This one.
Yeah.
The fourth column, right? Okay. 1, 2, 3, 4, 5. Okay, 5. So the way it is done, again, so what you did was for a specific point at xk and yk, you take the function first order partial order derivatives of that x. You would know, for example, in this example, if you do x, right? Let's do that actually. Let's do that. I'll get something to write on. Then we can do that together. So for this particular function p, if we use lambda p, I mean partial order derivative to x, what we get is 1440 minus 0.2x. That's it, right?
Minus 0.07y.
Yes, but if you take first order derivative for x, oh, there's okay, there's okay, I missed that part. Okay, and then what you do is you essentially get this value, and then your lambda k, which is lambda 0, is as 116, I believe, right? Okay, 160. So that you can get lambda 0 times this, right?
Yeah,
Which is this component. And then you have x0 is 0.
Yes.
So you get your x1 equals some number. 0 plus 1 over 16 times this 1440 minus 0 minus 0 because we start with 0, right? So you get your x1. Correspondingly, you can get your y1.
Yes.
And then the good thing is actually it's more complicated that you can figure out this this relationship. Lambda k equals to this. This is much more difficult actually. But here, fortunately, it already tells you that. So you can get your y1. So next thing that you would do is your lambda 1 is 1 over 16 times 1.2.
Yep.
So similarly, you should be able to get your x2 and y2. Okay, I haven't answered your question on that one yet. So once you get your x1 and y1, you can use your function to get your function value. In this case, it's essentially p x1 y1, right? P is this. Just
Yeah.
give the x1 and y1, you would find your p x1 y1.
Yes.
And then this one, I believe it is oh, so essentially we only got here, right? We're trying to find what's this.
Yes.
Yeah, let me do some study here myself, and then I'll try to send you an email today to everybody on this one. Okay?
Okay. Okay. Thank you very much.
Yeah, I'll send you an email to everybody on this page, on this particular problem.
Okay.
Okay. Any other questions from any of you? Or? Okay, that's the machine learning. Okay, someone give this. Okay, I'll send you an email to better explain this. Good night, everybody.